and welcome to another lecture. In this lecture we're going to talk about a snow load. This time we're going to talk about snow load on a flat roof. We got this roof right here. It's about 330 feet in the east-west direction, and the north-south direction is about 75 feet, and it has about 5 feet parapet wall. So we're going to do a design, calculate the snow load based on a criteria, and all the information is given, as you can see on the board right now. So what we have is the location of the building. It's in Lincoln, Nebraska. The surface roughness is B, and a risk category is given as 2. And the thermal condition, heated structure within and ventilated roof, is designed for 35 feet square Fahrenheit per BTU. And a roof exposure is partially exposed. Roof surface is a concrete slab with waterproofing. And the roof obstruction is just a parapet wall on 4 sides of the building, and it's about 5 feet tall. And then we have the roof framing. All structure members are simply supported. That comes in handy. And the roof is flat except for the slope localized area around the roof drain for rain drainage. All right. So before we go ahead, I'm not going to go over the lecture, how we're going to, what is the snow and how do the calculation, basically jump into the problem, and we figure it out this way. One of the things I want you to see is what I have on a board. We do a snow loads calculation procedure. Basically is 13 steps, and we're going to go through all those step one by one. So let's go ahead and go through step number 1, basically determining the ground snow load PG. Okay, the first step we're going to do, we have to find a ground snow load. To do that, we're going to go to this website called ASCE Hazard Tool, which is awesome. Really, they made things so much easier. Thank you, ASCE. And from here, we can go ahead and type in the location that you're looking for, which was Lincoln, Nebraska, I believe. And then when you do that, there it is, Lincoln, Nebraska. So now once we do that, we come back down here. We got to make sure we define the risk category, which was risk category 2. And we're looking for a snow load right here. And let's click View Result. And I want to get the summary right here. And this is what we're looking for. The ground snow load is 45 pounds per square foot right there. And another parameter we're looking for down the road is winter wind parameter W2, which is 0.55. These two numbers, we're going to look for it. And okay, let's continue. Go ahead to step number 2, and step number 2 is determine flat roof slope PF. To do that, we have to do multiple steps. So we're going to go to step, take a look what I have on the board. Step 2A, it's going to be determine the surface roughness category, which is given to us as a B. So I'm just going to write down the step 2. I'm not going to put down the information. Step 2A, and it's B. And then we're going to go step to 2B. It says determine the exposure of the roof, which is given as partially exposed. And 2B is it says determine the exposure of factor CE, and we can do that from ASCE table 7.3.1 with the surface roughness, as you can see on the board. CE is equal to 1, and write that down. CE is equal to 1. Step 3C is so we need to go to this table 7.3.3 to calculate the thermal factor. The information we have is the R value that we're looking for is about 35, between 30 and 40, which we don't have here. And the PG we have is between 40 and 50. It's 45, which you don't have here. That's why we have to do a compute double linear interpolation. I actually did a video. You can see the link for this video that I did how to do this double linear interpolation. It's on the link is on down bottom. Look at it. What I basically did, I'm not going to explain it here because it takes a little time. So we're going to go through here, use this equation, and basically put in this format, and right over here, use this format and use this and calculate it. And they came out to 114. And again, I have a separate video for this one. Go take a look at that if you're interested. So let's go back to the problem we have. Our CT comes out 114 using double linear interpolation. The next step we have is a step 2F. What we're going to do is calculate the flat roof snow load PF, which is given by this equation on ASCE, as you can see on the board. And we already calculated this value, and that comes out to be 35.9. We need that number. I'm going to just calculate that number here. PF is equal 35.9 PSF. Number 3, we're going to look for the minimum snow load PM. Since the roof is flat, a minimum snow load really should be considered, and we're looking at the ASCE, we can see on the board 7.3.4, and our PM, the max we can go is 30 pound per square foot. Because the PG, since PG, which is a 45, is more than 30. So our PM max become 30 pound per square foot. Keep that in mind too. So I'm going to write that down here. PM is equal 30. Same unit. So let's go to step number 4, which is basically they want to know the slope roof, which is basically balance a snow load PS. And we're looking for that, and our roof is flat, so our therefore CS is equal 1. So PS is equal CS times PF, which is equal 1 times 35.9, and that's equal 35.9 pound per square foot. So we're going to look at step 5. Step 5 is consider partial loading. They already given us that, so it's based on a given design data we have. The structure is simply supported, so there is no need for step 5. Step 5, no need, doesn't apply because the structure is simply supported. Step 6, consider balance snow load. Again, this is a flat roof, so that doesn't apply. Step 5, step 6 also not apply. Step 7, consider snow drift on a lower roof and roof projection. We don't have that, so that doesn't apply either. I'm going to put NA for step 7. And let's move on to step 8. Step 8, it says consider snow drift on adjacent to roof projection. And that's basically, we have the parapet wall. So now we have to go ahead and go to ASCE 7.71 for windward drift. And then that's going to be multiple step involved. Let me erase this part. Actually, maybe I can do it right here. Okay, step 8. And then we're going to go to step 8A. First, step 8A is calculate the snow density. What is a pound per cubic feet. I did that experiment because I live in New Hampshire. We get a lot of winter. A lot of time I used to get a snow and measure and see what do I get for pound per cubic feet. And it was different based on some snow was heavier than other snow. But this is really interesting. I like this part. What we have is to step 8, and the step 8A is from ASCE equation 7.7.1. We want to calculate the snow density. It's really interesting because I live in New Hampshire, and a lot of times we get a lot of snow. And quite often I go ahead and look at the snow. I have a box and measure them and find out what I get for pound per cubic feet. Of course, some stores has more water than other and packed more. But anyway, so the ASCE, this equation has said no. Use this equation, 0.13 times ground snow load plus 14. But it has to be less than 30 pound per cubic feet. So really, it says snow basically is about 30 pound per cubic feet. Remember, water is 62.4 pound per cubic feet. So you know how heavy snow is. So let's find out in this area, the snow, what it comes out to what. Gamma is equal 0.13. It was a 45 pound plus 14, and that comes out to be 19.9 pound per cubic feet, which is less than 30, and that will stand. Then we're going to move over to step 8B. Let me use different color. It says determine the height of the balanced snow load HB. We're looking for HB, and that's given to us by equation, of course, is PS divided by gamma, and our PS came out to be 35.9, and divide that by unit weight. Gamma was 19.9. This is a pound per square foot. This is a pound per cubic feet. So we got 1 foot left over. It's going to be on top, and that will give us 1.8 feet. So that is a HB. We need that number. Let's move to step number 8C. And that says determine the clear height from top of the balanced snow load to the top of the parapet or HC. We want to know what HC is, and our HC is so our H of the wall minus HB, and the wall was 5 minus 1.8, and that will give us 3.2 feet. What does it mean by here? I'm not going to put the number here, but right here, this is a 5 feet wall, and that's a 5 feet wall. And let's make this one to north to south direction when the wind's going to blow, and make this one to east to west direction which wind going to blow. And well, it's going to be actually this way because I'm twisting it around. So now the drift is a 5 feet, and the balanced snow is someplace around here. One thing we don't know, we got to calculate this height. It's going to come in like this, and it's going to drift out like that to some point. We want to find out what distance is. We already know this. We already know those stuff. We know the all the distance. We got to calculate these distance. We get to that in a minute. Going through these steps, you got to know the code. So you got to really read the code, and that's chapter 7. Step 8D, it says determine if the drift load must be considered. Yes, it could be, or no. So if you go to, there's a section on ASCE, see down on top of the board. It says from figure 7.72. It basically says if HC divided by HB, that's not good, HB is bigger than 0.2, and then it should be considered. So we have 3.2 divided by 1.8, and that's equal 1.8, which is bigger than 1.2. Yes, it should be considered. Then we're going to go step 8E. So the answer is yes, we're going to consider that. Step 8E equation, HD is equal 1.5 square root of PG by power 0.74 multiplied by LU by power of 0.7, and then multiply by W2. Remember at the beginning I said we need that number on ASCE hazard, and by power 1.7, and that number we already have from ASCE hazard website. So our LU, this is divided by, hold on, we're going to divide it by gamma, and everything is under here. So let's go ahead. However, remember, this is the equation, but look at what it says on ASCE chapter 7. It says, ASCE 7.8, it says, HD should be multiplied by 0.75. So I got to multiply this number by 0.75. Our HD is equal 0.75 times 1.5. Now time all this, let me change color so I can see it a little bit better. And that is a PG came out to be 45 by power 0.74 multiply LU. LU is a 75 because we go in this direction. 75 by 0.7, and this was 0.2 at the beginning that we calculated, time 1.7. No. That at beginning this was 0.55. If you go back to the beginning video from ASCE hazard, that was 0.55. And divided by gamma, and gamma was 19.9. 19.9, so we're going to get 3.2. No, HD is equal to 2.8. 2.8 feet. And 2.8 feet, which is basically less than HC, which was 3.2. 3.2. So it's less than that. Okay. So now we have our HD and HC. Okay, so let's go ahead and calculate the east-west direction wind, which is the same equation. So this was for north-south, and we want to do east-west, and gonna go to east-west, and HD is equal 0.75 times 1.5 times 45 by power 0.74 multiply 75, it's a 330. 330 by power 0.7 times 0.55 by power 1.7 divided by 19.9. And that's equal 4.7. So 4.7, it's bigger than our HC 3.2. Okay, we're good. So we know the east-west direction, the wind blow this way, it's give you a bigger drift. Okay, step 8F, we're going to do the drift width. I'd like to know how much the drift width is here, and this will be something set like this too. So the drift going to be coming like this, snow is going to come like that, it's going to be balanced, snow is going like that. Well, that's kind of, snow is like that, you know, straight line. Let's make a straight line. And let's figure out where is this and where is this. So we're going to go to north-south direction first. North-south direction, this is for the drift width. and the W is given by 8. Look at the spec. It says 8 HD, and which is equal 8 times 2.8 for this one, and that is equal 22.4 feet. So right here, this in here, it's going to be 22.4. I will redo this in a minute, just for now. And then we're going to look at the east-west direction, and W is equal 8 times 4.7, which I already calculated here, right here, and that comes out to be 37.6 feet. So this right here is this distance right here is 37.6. Now we're going to go to step 8G. We're going to calculate the drift load. And PD is equal gamma times HD, which is equal, gamma was 19.9 multiplied by 2.8, and that will give us 55.7 PSF, pound per square foot, and this is for northwest, north-south direction. In the east-west, let's change color. East-west direction, PD is equal 19.9 times 4.7. No, we gotta go with HC because this is more than HC, so we gotta go with HC. So HC is 3.2, and that is 63.7 pound per square foot. Same unit. Step 8H it says determine the total snow load at the face of the parapet. What is the snow load here? What's the snow load there? So P total is equal PS plus PD, which is equal, PS came out to be 35.9 plus 55.7. So P total, and that's for a north-south direction, is equal north-south, comes out to be, or not to be, 91.6 pound per square foot. Now in a east to west direction, this is good, how come? That's not good. Is same thing, it's going to be 35.9 plus, it was 63.7. 63.7, so that comes out to be 99.6 pound per square foot. This is basically, as we go to step 9, Step 9 doesn't apply, which is basically is consider sliding snow. We don't have. Step 10, consider rain on a snow load. Oh yeah, we gotta calculate this. Per ASCE section 7.10, you can see on the board, we gotta look at the based on the location. Let's write this down. Step 10. And that's going to be our PG is less than our Pmax. So therefore, and also PG is bigger than 0. Therefore, on a roof with a slope, on a roof with slope less than should be A, I don't know, W divided by 50, and PG is 45. It's more than this actually, so it's, we have 45 more than 30, and it's, we know it's more than that, and the roof doesn't have the slope is less than WI50 because it's a flat roof. So therefore we need to add a rain surcharge because this is a flat roof. The spec call for add additional 8 pounds per square foot for a rain surcharge. So you're now going to snow on top of the roof. It rains. I know you got a drainage, but still you got extra 8 pounds to it. Then we're going to go to step number. What's step number 10? Step number 11. It says consider pounding instability. That's something you really should do some analysis if you're going to have a deflection. We did that in rain load. See if you have a pounding. If you don't have it, you don't have an issue. So go back to that, and then consider existing roof, which doesn't apply, and 13, consider snow load on an open frame. That doesn't apply, and that's it. But let's go ahead and do our chart here for a second. Let me erase that. So here's our final result. This will be north, south direction, east, west direction. Which was the drift load was 37.6. Erased it? Yeah, I did. The load came out to 99.6 for a drift, and for the balance was 35.9. Same up here. For north to south was 91.6, and going to balance 35.9. This is pound per square foot. So when you do your load calculation, you might have to multiply by the turbidity width for a beam or whatever calculation you do. Anyway, don't forget about that. You got an 8 pounds per square foot for the rain. I hope you liked it. Again, to encourage me to do this kind of stuff, I do it for you guys. Give me a thumbs up. I love your comment, and that will encourage me to do more videos like this. Take care of yourself. Have a good day.